The physical design flow is the engineering pipeline required to translate a logical, text-based chip design into a physically manufacturable layout. This process involves the precise mapping of billions of individual logic instances onto a constrained silicon die. The final output is the GDSII file, the industry-standard geometric database containing the exact polygons sent to the foundry for fabrication. In a hardware description language like Verilog, a transistor acts as a mathematically perfect switch. In physical reality, that same transistor is surrounded by hostile physics. Flawless RTL code cannot be fabricated without rigorous physical implementation. This flow is the only bridge between theoretical architectural intent and a functional chip. The primary goal of physical design is balancing power, performance, area, and cost, known as PPAC. These metrics exist in constant trade-off. Maximizing performance, like increasing clock speed, inherently degrades power efficiency or expands die area. While older nodes allowed for more linear scaling, advanced nodes like 5 nanometer and 3 nanometer present a significant physics wall. Extreme interconnect resistance, parasitic capacitance, and severe thermal density at these scales shatter the assumptions of traditional sequential design pipelines. Achieving design closure at sub-5 nanometer dimensions is an NP-hard problem where fundamental material physics frequently counteracts the engineer's design intent. Floor planning establishes the chip's structure. We define die dimensions, snapping large macro blocks to the perimeter, leaving the core open for standard cells. Next, we construct the power delivery network, a dense metal mesh distributing VDD and VSS supply rails across the die. At the 5 nanometer node and below, power integrity becomes a primary challenge because the metal wires forming this mesh are incredibly thin and highly resistive. This resistance causes IR drop. We must account for static IR drop, the average current draw, and dynamic IR drop, caused by transient spikes when logic switches simultaneously. High current densities can also trigger electromigration, a physical displacement of metal atoms that can eventually cause open circuits. A local drop in voltage causes gate delay spikes. If a gate switches slower than intended, it creates setup timing violations that can be impossible to fix late in the flow. Without a robust power mesh, the chip risks physical degradation and complete functional failure. During global placement, the EDA tool determines rough locations for millions of standard cells, seeking to minimize the total wire length required to connect them. Legalization and detailed placement follow, snapping overlapping cells into strictly defined rows on the placement grid to meet foundry design rules. Placement must be timing-driven, meaning sequentially related logic gates are placed physically close to one another to minimize signal travel time. However, tight clustering creates local routing congestion and thermal hotspots that are difficult to mitigate. Placement is therefore a necessary compromise between clustering for performance and spreading cells apart to ensure the design remains routable. Clock tree synthesis builds the physical distribution network strictly required to deliver synchronized timing signals to every flip-flop and register. A traditional H-tree architecture, seen here, attempts to deliver the clock symmetrically across the die. The goal is to minimize clock skew, the difference in signal arrival times between registers. If the skew is too high, buffers must be inserted to fix hold time violations. Conventional trees often fail at advanced nodes due to extreme sensitivity to process, voltage, and temperature. To counter this, engineers now use multi-source clock network synthesis, a hybrid tree-driven mesh configuration providing better on-chip variation tolerance. This involves a complex assignment process where sinks are connected to specific multi-source tap points based on arrival time and loading. By grouping sequentially related sinks to the same tap driver, engineers can minimize local clock skew without the power consumption of a pure clock mesh. Delivering a synchronized gigahertz clock across a dense die while remaining within a power budget is a major bottleneck in high-performance design. In detailed routing, the EDA tool connects all placed cells using the metal stack from the lowest M0 layer to the upper global layers. The density of the lowest metal layers is so high that strict geometric rules are required to prevent electrical shorts and spacing errors. At 5 nanometer and below, the resistance-capacitance parasitics of these tiny wires entirely dominate the total timing delay of the design. This reality necessitates design technology co-optimization, or DTCO, where the manufacturing process and digital design rules are developed in tandem. Foundries use DTCO boosters, such as buried power rails, to move power delivery below the transistor layer, freeing up metal tracks for signal routing. Physical design at advanced nodes requires this direct co-optimization between digital layout and foundry-level material physics. The final stage is sign-off, the final validation required before tape-out. Static timing analysis provides the mathematical proof that no setup or hold violations exist under any possible operating condition. Physical verification, including design rule checking and layout versus schematic, ensures the foundry can successfully print the layout. Because of advanced node physics, the traditional linear physical design pipeline is no longer sufficient to guarantee timing closure. Late-stage routing parasitics frequently invalidate early-stage placement assumptions, leading to recurring iteration loops. Modern industry platforms address this through monolithic fusion methodologies, which integrate synthesis, placement, and sign-off into a single environment. These engines run concurrently on a shared data model, using machine learning to predict routing congestion and close timing faster than a sequential flow. Ultimately, the RTL to GDSI flow has evolved into a single, multidimensional optimization problem. Achieving a functional sub-5 nanometer chip requires the simultaneous management of electrical physics and autonomous AI-driven EDA platforms.